So I posted on Slack how to go about doing this. We've done it before, but let's open up a terminal and go to the science data generation repo. Copy that one. And then we do a git clone. So we can see that it's hopefully working. Hopefully everything will be working here. One is never sure. Now we can see we have this folder here called Science Data Generation. We'll go in here. We'll go into the notebook. Also, please, if anything goes too fast, just let me know. We'll slow down. I'll try to keep it pretty level. So we have this amazing data set from ICESat-2, but also we have plenty of other data sets as well. So I'm just going to talk a little bit about a simple workflow to that people can use just to kind of like go from point data to science products that you can use for your research. And this is a lot based on the CAP toolkit that me and Fernando have been developing for a couple of years. And it comes out of the need in the sense of like standardizing a little bit. A lot of the time, at least in cryosphere and altimetry, a lot of the stuff is, the wheel is reinvented. And a big, I would say, hinder for people, especially PhD students and even postdocs and researchers to get into the field. It's just kind of like they have to reinvent the wheel of like, how do I process the data? What corrections do I apply? So this is in a sense a little workflow to show people how to easily get started with doing research using kind of like a prep package for you. And this is also research that it's ongoing, that me and Fernando are using this daily. So hopefully everything works like it should, but if there's anything that you find out when you're using it that is not working, please let me know, or something that you feel is missing. And that's something that we can always add or change. So like I said, we're just going to present a simple workflow here, how to use that to generate rates of elevation change and time series, and go a little bit looking at a DEM as well, and then do some quality checks. So some of the learning objectives, just get familiar with the simple processing flow, understand what the important parameters are, limitation and bottlenecks, some tuning of the parameters, how we do gridding, filtering for the different geophysical entities. Right? So this is let's see again. Oops. So this is just a figure of from ICESat, some spanning from 2003 to 2009. And it shows the area that we're going to work at, like Pine Island Glacier. You can see the drawdown here over the couple of years that the measurements were done. So this is kind of like the area we're going to focus on. So here's kind of like the long-term trend currently what we're seeing in Pine Island. So you can see that's almost like constant drawdown. And it's been pretty consistent, and it's even starting accelerating in the last 10, 15 years. But yeah, let's go through just kind of like the data products and general approach. So we'll use ATL6 for this. The ATL6 data has been read in and flattened into files that was shown by Fernando showed that approach a little bit. So in principle, the only thing we need for this type of tutorial is we need long, lat, time, height. And with that, we can compute time series, we can compute rates of elevation change, we can construct a DEM, and we can do some quality control. Actually, for the quality control, I should have added needed an orbit here, which has not been updated as well. So in the future, for at least for ICESat-2, Ben has prepared all these nice products for you with ATL, starting with ATL11 and also an ATL6, of course. But sometimes when you do your research, you might want to be something that might not fit you perfectly in the way you want to do research with the standard products that come available. So one nice thing maybe to do is like to use some other way of kind of like getting to what you want to do, like what you want to look at, like the temporal resolution you want to have or the spatial resolution. So this is like what we're going to talk about a little bit here. But also, the approach that I'm showing here works on pretty much any generic altimetry data set. So you don't have to do, it can be used on ERS or EMISAT or CryoSat. So it's not just for one, it's just not built for one thing, it's built for kind of like a range of data. So you can see here, we're gonna start like in the end of 2018 and go up to April this year. I'm gonna focus on pig here. So we're gonna just start loading some packages here. So you can see there's a lot of functions in what's called utils. It's over here, you can see that here. So the functions or the programs we're gonna use today, I put them actually in the folder here. They're available in the CAP toolkit. And once this tutorial is over, I'm gonna go and update CAP toolkit to put the latest in. So I put them here for now, just to make sure that everything works properly. And if there's any issues that we can go and take care of that. But yeah, so we're gonna read some of these libraries in, and we're gonna have a look at the data. So the data is in the tutorial data folder called gradient time series. We can have a look there. And apparently that doesn't work. It's always something that doesn't work. So if we go up here, science data, oops, tutorial data, gradient time series. There's two files here, one called ICESat-2 heights pig A and ICESat-2 heights pig D. And these are files that are separating ascending and descending orbit. This is something that comes out of read ATL 6. So Fernando was talking a little bit about that before in his tutorial. So read ATL 6 is a program that I wrote a couple of years ago to work with ICESat-2 data. And one of the things that it does is actually takes the ATL 6 files and separates the beams into its own data files. So with that, you can actually have a look at separate the beams, and you can look at the beams individually. And one thing it also does is it adds a or a D in the end of the file to let you know if it's an ascending orbit or a descending orbit. That's important later on. I don't know why this is not working. It actually worked just before. So if somebody actually knows why it's not working, that would be great. I'm hoping this is not going to be a problem, because I checked it just a couple of minutes ago and it actually worked.
Johan, are you sure you clone your repo on your home directory?
I hope so. It should be here.
Working for me here, so.
Does it work for you?
Yes.
This is very weird. So I will have to see if I need to reinstall this again.
Johan, could you narrate off Fernando's screen?
Yes, probably. If Fernando shares the screen, we can do that. So it worked literally 2 seconds ago, so just a couple of minutes ago. So Fernando, would you mind?
Yeah, give me a second.
Yeah. It's good it works for everybody else except me, who's actually showing it.
Actually, I was having the same problem, but after changing the relative directory to /srv/tutorial data, it's working. If you're using absolute directory.
Yeah. So Fernando can go there. Yeah, great. So so yeah, here again you can see the files. So it's ICESat-2 heights pig A, ICESat-2 pig D. And thanks Fernando for helping out.
Yes, I'm setting up things here. I wasn't ready to.
No, I don't know why this happened, so I'm equally as confused. So so let's we have these files now, and then we want to just have a look in them, right? So if Fernando, if you run the next line there with the H5LS, that one, yeah. So here you can see that we have a couple of variables. We have the height, we have the lat, we have the long, we have the orbit, and time in years. So this is really the only thing that we need to work with this data. And if we read that into memory, can you do that, Fernando? Oh, yeah, we have to load the.
Yeah, my bad. Didn't load the needed library. There we go.
Let's try again. All right. So this might take a little bit of time if everybody's doing it at the same time. So maybe people just want to have a kind of look along a little bit for now. These are not majorly big files. They're only a couple of 100 megabytes, but if everybody's using the system at the same time, we might have some issues.
There.
Fantastic. So now we have that. We're also going to read in like a little masking file that we're going to use later. And then, so now we have all this data read in, right? So let's have a look. Let's plot the data. Let's plot the ascending heights here in this case. So here you can see that this is the area we're working with. This is a bounding box of Pine Island. And if you go to the next one, we'll zoom in a little bit. And here you can see this beautiful picture of Pine Island. You can see in the bottom here, in the blue, you can see the lower elevations of the ice sheets going out to the shelves. And then you can see this entire trunk colored by the, filled in by kind of like the yellow colors here. So this is ascending files separated. So if we have descending files, they'll go in the other direction. So one of the reasons why we want to separate them, you can run that also, Fernando. So here we have a height range from 10 meters to around 1400 meters. So if we look at a histogram, which is the next one, if you look at the histogram here of elevation, you can see that we have a wide range of elevations here for this trunk, right? So one thing that we want to do here to get a time series is that we have to remove this static topography to kind of flatten everything out. So the time variable signal is superimposed on top of this static signal of elevation, meaning that if we want to compute a time series, compute rates, we have to remove that. But that topography varies in space. So one way of doing that, if you go down a little bit further, Fernando, is that you can detrend that surface. And that's kind of like what we're going to start about a little bit more. So if you go up a little bit more, I'm just going to talk a little bit about Cap Toolkit here. If you go up a little bit.
Up?
Can you go up a little bit in the beginning?
Yeah.
So yeah, so I'm just going to talk a little bit about Cap Toolkit here. It's a collection of command line programs that me and Fernando have been writing over the years. And these are something that we use every day in our work. And they've proven essential in the way that we work with data. So it's just a long, sweaty road to get there. But so the functions we're going to use here, or the programs we're going to use here, is something called fit topo, merge, interp gauss 3D, read ATL6, which we already talked about, then x over dot pi. So fit topo is the program that we're going to use to remove this static topography to get at the time variable signal. And if Fernando goes down a little bit, we also have some help functions here as well that we're also going to use that are also available to you in the utils to do some coordinate transformation and some interpolation, reading to files, some outlier rejection schemes. But so as Fernando's already pushed on cell 12 here, Python fit topo.py, here you can actually see the inputs. So to the program. So what the program does is actually takes a grid and puts that on top of your region of interest where you have the data. And that grid is defined by the spatial resolution here, dx and dy, in the D option. So by setting the size of the cells and the search radius, it kind of like for each grid node, it searches around and finds the data and it fits a mathematical model to it. And this mathematical model is then removed. What you're left with at that cell is then residuals that only varies in time. So there's some different types of inputs here. So you have the dxdy, that's the spatial resolution, the radius, the search radius of how far you want to go out to kind of get enough data. The number of relocations is just the, applies a random walk type of approach to find the center of the data. So if you have like a long tracks or reference tracks and your grid node is, your track is kind of like at the edge of the search radius, it kind of like moves the center on top of wherever you have the maximum data density. So it kind of like moves itself around and places it in the middle to get, to improve the fitting. It gives you a little bit of other number of iterations, number of observations to be used, but then also the most important here is K, the order of the surface fit. So either you have like a bilinear model, you fit a plane, or you have a biquadratic model, which fits a higher order surface. And in the end, if none of those works, there's a average height component where you fit, where you get the slope in the X direction and the Y direction separately. So you can see that this doesn't really need much. You need X, Y, T, and height. Actually, we actually have included time in the model as well. So this is to be able to reference the surface to a given time. This is especially important when you separate ascending and descending tracks. So you want them to go through zero, or like you want to be referenced to the same height and time. It's also good to do when you have like, you want to make a DEM from different time steps, for example, using data that has several years of data in it. But yeah, so if Fernando can go down here a little bit. So here you can see the input of the program, right? So you have the D option here. We're not gonna, please don't run this right now. You're probably already doing it, but it's just a matter of like, it takes a while for this to run. It's like each of these are like 7 minutes. So I'm just gonna go through a little bit how to use the program, and then people can play around with it later on. So I already have read in, or I already have made you a ready dish to eat, so to speak. But you can see here that I'm putting a 1 kilometer grid here. That's the D option. I'm using a search radius of 1 kilometer. That's the R option. I'm doing 3 iterations, minimum number of observations here. And then the P option here, that's a verbose option. So that's something when you run this program and you play around with parameters to get a good fit. This is kind of like an important, I think, way to discuss or to learn which one, how these parameters actually work, so it gives a good result. So Fernando, can you run this? Just press enter. So you can see it reads in the file A, and then prints you a couple of outputs here with the parameters you selected. It's now loading the data, converting long lag to stereographic, polystereographic, and it's building a KD tree. And in a second here, it will start spitting out these in the verbose mode. It's spitting out these values here. So you can see, for example, most of the time you're using model 1. We have over 500 observations, usually almost close to 1,000. You can see the surface slopes that's estimated as well. And then one of the most important part are the residuals. These residuals indicate if you're doing well or doing poorly, depending on what parameter you're using. So you can tune the parameters. You can stop that for now if you want. You just press the stop button here for that cell.
I think I will have to kill the kernel.
No, it's up there. It's just a little bit up, just above the square. Up there on the terminal window. There you go. Yeah. You might have to press it a couple of times. No, that works. So if the residuals here are very large, you're probably not, the fit is not probably doing really well, right? So you might want to switch over those, like change the resolution, change the search radius, and so on and so on. That's just a good way to understand how to get good results out of that one. So if you're looking at the next step here, the LS tutorial data gridding time series, I have prepped data for you. Can you press that one, Fernando, the next one?
The next one?
No, the next one after that.
Ah, okay.
Yeah, that one. Yeah. So in here, so when the program is done running, it gives you, it appends the name topo in the end of your file name. And if you actually inspect the file now, H5LS, the next cell, if Fernando can press that one, you can see all of these parameters or variables have been added to the file. And these files are actually, or sorry, these variables are spit out by the actual program. So you can see here you have hrest, that's your temporal residuals. You have hmod, that's actually your mean height, reference to a specific time. mdeg is the degree of is the model used. Slope x and slope y are the long and across track slopes, and so on and so on. And so we are actually interested in the hrest variable here. So if you, Fernando, go to merging of files. So we've done this now for both ascending and descending. Now we want to put those back together. So this is a nifty little program that Fernando put together, just kind of like stacking H5 files into common files. You can select variables and so on. So we're going to run that now and merge the ascending and descending files into a common file. This takes a little bit of time depending on the system. So we can see that it's reading the file.
It is also because it's doing it in chunks to avoid loading all the data in memory. So it takes longer, but guarantees that it will be done.
Yeah. And it can handle large data sets, which is really good. So we do this on Antarctica and Greenland and places like that. So using 30 years of data. On my laptop, it works pretty fast, but as we're on the system, it takes a little bit longer. But we can talk a little bit more while this is happening. So one of the most important things I feel like if you want to work with these workflows is just to kind of like get an idea of what works and what doesn't work. To get an idea of what parameters should I choose? What's the resolution? What will give me good results? What do I want to look for? So I think everybody's running this at the same time. That's probably why it's taking a little bit longer. So this is a file that we actually need. I didn't make this, I didn't pre-make it, so to speak. So hopefully that will go soon work. So if people are doing this themselves, can they kill that just to make sure that not everybody's trying to do it at the same time? So this is typical. You prepare a tutorial and everything works 15 minutes before. You download it, you test it, it runs perfectly, and then you do it again, and then nothing works, always. So Fernando, let's do this. Can you go and copy the path to one of these files, like ascending only, and then we'll just read in the bottom there, instead of merging the two.
Ah, gotcha.
Yeah.
They want to work just with this guy here.
Yeah, just take the ascending one. Yeah, just copy paste that one and read that one in instead.
How about this? Is the same name?
No, it's not in the same folder. You have to take the entire path. So tutorial, data grading, yada yada yada.
Yes, probably you need an absolute path, right?
Yeah, you can actually have you can just copy paste the path that was already that you saw there. Not sure if you.
Hold on, I have 2 copies here.
Yeah. Then you have to kill that. Kill that cell again.
It's not killing.
Try a couple more times. You just press it a couple extra times there. It usually works.
It isn't. So in worst case scenario, we can restart the kernel and
yeah.
keep cells.
Well, just actually, let's just restart it. And then you just read in the libraries on top here. And then you can go directly to that file again.
Even to import the libraries is slow.
Yeah, I don't know what's going on. I had an issue where when I was running it, that it just stopped working and then I had to restart the entire thing.
That's what I'm doing now.
Yeah.
And it seems it's unresponsive.
That's super weird.
Maybe I'll try something else. Yeah, there we go. However, this is still green.
I have no idea. I'm not getting actually, can't even log into the.
And my terminal is not working either. So
yeah. I can't even log into the Jupyter hub anymore.
yeah, you see? Okay,
Yeah.
so this is not working. I probably need to get out of here.
So we may be having hub issues.
Yeah.
Just seeing if your others on Slack saying the same.
So I can try log out and log in again, maybe. So nothing on my Jupyter lab. Okay, now it opened the instance.
So I'm not sure if it's because everybody's running at the same time. So that might be an issue.
No, there is something else. So yes, all the applications on the Jupyter lab here are unresponsive and the kernel seems to be on. So what happens if I get off here? You see the wheel there, it's unresponsive. Are others able to run their notebook? Because it's not even letting me log out.
There seems to be some for some people and some it's not working for.
I would suggest we take our break now and then we can get our heads together about.
So sorry everybody for the problems here. I'm just gonna start where we kind of like left off, but I'm just gonna show you this picture again of the of the elevations over Pine Island. So this is how it looks like when you have all these elevations, right? Ranging from 10 meters to 1400 meters. So what we did with the CAP toolbox, used Fit Topway here to remove that static topography. And we tried to merge these ascending and descending files, which now actually worked. So one of the good things with Fit Topway is that if you put, for example, the same time span, in this case, exactly to 2020, they're all aligned in height. So they're referenced to the same height at the same time. And that's important because one of the reasons why we take those process ascending and descending separately is that once you try to remove topography, is that you might have a bias in between ascending and descending tracks, and it's effectively like kind of takes that issue away. So what we did now, we merged this data. Now we have one file containing both ascending and descending, and we read in the variables that that we want to have a look at. So we're going to look first. We're going to look at the residuals that we did, and of course, we go. I'm not sure why that happened. So here's the residuals out from the removed static topography. And now this is should just be varying by time. You can see it's pretty noisy. So there's a lot of like, a couple of bad solutions in there. So let's look at a histogram. You can see, a lot of weird values. We have a big spread of values. So let's do like a quick global threshold of 10 meters. So we'll do that. So we remove everything that has an absolute value larger than 10. And then we fit that again. Yeah, here we can see actually we have a nice kind of like residual histogram, decent mean, decent standard deviation, and rejected with that 10 meter threshold, roughly 8% of the data. So in the utils function, we have this transform coordinate function. This is based on PyPro. So this is what we use to use transforming between different projections. So in this case, we want to go from long and lat into subpolar stereographic 3031. So we'll do that. And takes a little bit of time. There's a lot of data. So another thing that we want to do then is that we did a global threshold, but there's also a lot of like local outliers. So what we want to do is we apply a spatial filter. So this spatial filter here divides up the region in 100 by 100 kilometer bins. And inside each bin, it applies a 3 sigma threshold. So let's run that one. And then we'll print again. We can see that, we went from 23 to around 18. Standard deviation went from almost 100 down to 66. So another 10% rejected, which is really good. And then what we left is this nice looking residual histogram. So let's plot that and see how that looks. And now we get this like more clean residual space. So a lot of the errors we saw before are now gone. So it looks pretty clean. You can probably see some signal over here. And we can make a quick time series of this. Now we've removed all the static topography. Let's look what happens if you just plot time versus the residuals. And this is what you get. So you get the point cloud here, and then I binned the data using a median in red. And you can see that there seems to be a trend here in PIG for the last year and a half. So what we can find is that on average, it's around 0.5 meter per year. So one thing you should note here that we're using point data, and that has an issue when you want to compute trends and stuff like that, because data might be irregularly distributed all over the place. So you might want to grid this to get a proper value. So that's what we're going to do. We're going to use spatial temporal interpolation. It's called Interpolation 3D, or you might want to call it 4D if you want to. But in principle, this takes x, long lat, height, time, and then error. And what it does is that it uses an exponential weighting in time and exponential weighting in space. So it's just a simple interpolator to go from point data to grid data. So I actually ran this for you already. So we selected the overall time here. This is like a fraction of a month. So if I put 1 here, that's 1 month. So this is 1/8. So it's half a week pretty much. But yeah, so we ran that. And what we get is this data cube. If it goes too fast, let me know. I'm trying to gain some time here. So we save this into an H5 file. And you can see it with the structure in the file that we have these dimensions. This is time, this is space. So inside of this cube, we have CPRED, CRMS, and CNOBS. So that's the predictions, the interpolated values at each node. And that's the value error at each node. And that's the number of observation used in the solution. So all right, we read that in. We kind of want to mask this now. So now we're going to use the mask. I think actually this was read in. Yes, it was. So we're going to interpolate this mask to our region of interest here and transform that. Apply the mask and then we'll plot it. So here's the gridded solution, right? So this is now time. We can step around in time here. So that's another time step. Do 50 here, another time step. So you can see actually how the surface changes over time. So how does this time series of this cube looks? So we can make a quick time series of this. We'll do that. And then we'll plot that. So what you see here is that the interpolated time series is around 0.4 versus 0.47. So here in the red here, you can see the interpolated time series, and then the black is just a linear fit to the data. But they're pretty much the same rate. So just looking at this more in detail, here you can actually see the elevation signal. So we used a couple of steps. We actually made a time series. We took the point data, we interpolated, and now we have time series. So we have a data cube that we can work on. So one thing that a lot of people want to do, they want to find what's the elevation change over this entire time span. We did this by fitting a polynomial to the data. But we can also do that in space as well. So let's start having a look at that. So I'm just going to loop through each of the cells in the cube and fit a polynomial, linear polynomial to it. So we do that. We apply a generic filter. Generic filter is very nice. It just applies any type of function that you want to it. And then here, now we have elevation change rates for Pine Island. So here's the classical drawdown signal that we found. Actually, if you look in the top picture there. So we used a few steps. We actually produced an elevation change map of Pine Island for the entire ICESat-2 data set. And this corresponds roughly to a volume change of around 40 cubic kilometers a year, which is, I would say, pretty close to what the current long-term rate is for this region. So I'm gonna see if I can quickly step through here. So you might want to construct an elevation model as well using the topo. So this H mod here is the intercept of that model. So that now contains the mean height that we removed before. So this mean height is now centered to a specific date. So all that data with different time, all that data spent 1.5 years is now referenced to the same location or the same time, which means that all the elevations are referenced to 2020. So we can do that, just plot those. We can see that, here we go, it's pretty noisy. We use the outliers that we identified in the previous step, remove those. And what we get is this nice looking point data set again. So I'm just going to do some steps here. This is a make grid function. Let's say we want to make a DEM of 1 kilometer. Actually, just for the sake of argument, I'm going to make this 5 now. So, and then we have a mask here. Inside Cap Toolkit in the utils functions, there are these kind of like lower level interpolation functions that are based on the common ones that's available as big programs. But these are for like quick analysis of data in your notebook or whatever you want to do. They're very handy. And we're going to use those now. I put some notes here about different interpolation algorithms. You can read about that. We're going to use some collocation kriging here called interpolation. So that's what we're going to run. So you give it a couple of inputs, X and Y and height. You give it an RMS. This is going to be added to the diagonal, which means that you add error. So that kind of like if you have error observations together with your heights, you can add those here. And we're going to use the 20 closest points. We have a correlation or a maximum search radius of 20 kilometers, and then a correlation length of 5 kilometers. And the correlation length kind of controls like how much of the data that's closest to you is going to affect your interpolation. So let's run that. Hopefully, as I change to 5, it went really quickly. So one thing that happens here, everything here comes out as 1D arrays. That is an active choice that I made because sometimes you might want to do other types of interpolation, point-to-point interpolation. So you can just put in an array here of any type of values that you want. So let's apply a mask and then plot that. And here's your DEM. Now you made a DEM. And if you increase the resolution, it looks even better. So this is now built on data that's spanning several years, like I said before, but as we reference them to the same time, they can be stacked together and you don't have to worry about if you're using data from 2010, for example, or 2019, if there's an elevation change in between those two. So we're taking care of that. So I'm just going to talk a little bit about quality assessments using crossover analysis. So this is an old figure from 1989 from Jay Swally. So crossover analysis has been pretty fundamental in studying the ice sheets and also to study the quality of the data. So it's pretty much two satellite tracks crosses each other. We find the height at that crossing and that we can compare those two heights and create a difference. So that difference, you can build time series, or you can actually separate the DTs, so you have short DTs, and that would allow you to study the quality of the data. So that's what we're going to do. So we actually have a crossover program that you guys can use. Not going to run it right now. We already have a ready version to use, but so this pretty much takes your orbit, lat long, time, height, and then some extra parameters. You can just use these ones if you want to. And with this, you can actually compute satellite crossings. So it uses an internal tiling scheme. So if you have a region that we have currently right now that gets divided into smaller regions that are used to compute the crossing to increase the speed, you can choose between linear interpolation, cubic interpolation. You can also run it in what's called tile mode. So you can take, if you have Antarctica, for example, you can divide it up into tiles. We have a programming toolkit called tile.py. If you give this tiling program the same extents for ascending tracks and descending tracks, this program can read in and match two tiles, and then it will cross those two tiles together. This helps also to speed things up. But so we run this. This takes around 2 minutes to run, so it's not bad, but I don't want to do this now with everything that's going on. So I'm just gonna show you the output here as I already have a ready-made file. And also you can play around with these parameters. I kind of like made this for speed. So if you want to, you can make it even better. So we'll increase the number of crossovers that you get. But currently it's running at in 100, selecting if data is further away than 100 meters, it's not computing the crossover. We're tiling it to 10-kilometer tiles. We're subsampling using every 20 points. This also helps because you want to cross two tracks. If you for ICESat-2, it's like every 20 meters. So to find a crossing, you do kind of like a least squares inversion to find the crossing point. So if you remove points there, you will still find the crossing, but it will be faster because you don't have to invert as much. But anyway, so let's have a look at these. So here you get some the output variables here. So you have a DH elevation, you have some DHT, DT year. Here's the height 1 and height 2. These are the values at the crossing node, and these are the times at the crossing node. So let's read that in and have a look at it. So here's the crossover data. I've selected DT larger than 6 months to get more of the elevation change signal here. So you can see actually the outline here of Pine Island again, the drawdown. And these are, like I said, crossover locations where ascending and descending tracks intersect. So if we want to have a look at the actual crossovers as a function of DT, that looks a little bit noisy. So what we do here, we select everything that's ±5. And then here's what you get. So DH versus DT. So you can fit a line to this. And you see that the trend here is around -0.4, which fits really well what we got from fit topo and the interpolated data. So that tells us that we're doing the right thing because we've seen this now from 2 different methods, which is really great. So one thing to check quality of the data is that you subsample the DT. So you only keep DTs that are less than 30 days or even smaller. It can be a week or a couple of days. It's just a matter of how many data points you end up with. So we can do that. So let's select everything that's an absolute difference less than 5 and a DT less than a month. We're gonna keep that. And then what we get here, this histogram of the age less than 30 days. So let's check some statistics here. So we can see that the difference between the ascending and descending bias is 1 centimeter. This is great, actually. This is very great. And the error is only 11 centimeters, roughly, like the spread of this histogram. And Pine Island is a pretty rugged place. It has a lot of terrain. So due to the small footprint of the laser, we're getting really good results here. This is kind of like one of the tougher areas to look at. Another way to look at how well we're doing is to look at this bias as an error as a function of surface slope. So we'll read in the surface slope here, which is just a TIFF file. We'll interpolate the slope values to the crossover locations in this variable slope. We'll bin it as a function of slope for these two parameters. This is just a nifty little binning function. It reads in the X and the Y and bins it and comes out with some statistics. So here's the bin slope value, the bin bias, and the bin error. You can plot these. So we can see that over the bias doesn't vary that much over the entire surface slope. Look at these values here on the plus minus on 6 centimeters, which is nothing. It's varying around 0. If you look at the error as a function of surface height, again, very, very small. It's about 18 centimeters at the maximum. If you compare this to radar, this will be meters. So you can really see how well ICESat-2 is doing over rugged topography. So just to get an idea of how big the slope is here. So the slope ranges from like almost 0 to almost 4 degrees surface slope, with an average around 0.4. So one should remember that for radar, anything above 1 degree surface slope is really difficult for the radar to handle. But here we can actually see that we can do great things with ICESat-2 just by looking at the quality of the data here using crossover analysis. Again, I had to go through this a little bit quickly, but here is some homework maybe if you guys want to do something. I would suggest like you play around, you download the data maybe to your local machine, because currently it's in the science or the tutorial folder, so you only have read permission there. But if you copy paste that to your local, you can play around with fit topo and the interpolation and the outlier editing, change these parameters to have a look at how they affect your results. So for example, fit topo, I used 1 kilometer. You can go even further down to, like, say 100 meters if you want to. And you can see how much that affects your results. It'll just take a little bit longer time. But I